In the vast expanse of the cosmos, a faint glimmer from a distant world has ignited the imaginations of scientists and dreamers alike. Proxima B, an exoplanet orbiting the red dwarf star Proxima Centauri, just 4.2 light-years from Earth, stands as one of the most tantalizing discoveries in a modern astronomy. This Earth-like planet, nestled in the habitable zone of its star, has sparked a global quest to answer one of humanity's most profound questions. Are we alone in the universe? Recent detections of unusual light emissions from Proxima B's dark side have only deepened the mystery, hinting at possibilities that range from natural phenomena to the staggering prospect of alien technology. As we stand on the cusp of a new era in space exploration, Proxima B beckons us to unravel its secrets, challenging our understanding of life, the universe, and our place within it. The discovery of Proxima B in 2016 marked a turning point in the search for habitable exoplanets. Located in the closest star system to our own, this planet is not just another distant speck in the sky. It's a tangible target for scientific inquiry. Its proximity, combined with its Earth-like characteristics, has made it a focal point for astronomers seeking to understand the conditions necessary for life beyond our solar system. However, Proxima B is no paradise. Its environment, shaped by the volatile nature of its host star and the phenomenon of tidal locking, presents formidable challenges to habitability. Yet, it is precisely these challenges that make Proxima B so compelling, as they force us to rethink what life might look like in the cosmos. In this comprehensive exploration, we will delve into the science, mysteries, and possibilities surrounding Proxima B. From its physical characteristics and the peculiarities of its red dwarf star to the cutting-edge technologies driving our observations, we will examine why this planet has captured the attention of the scientific community. We will also explore the implications of its strange light emissions, the technological hurdles in studying such a distant world, and the potential for groundbreaking discoveries that could redefine our understanding of life itself. By the end, you will understand why Proxima B is not just a planet, but a symbol of humanity's unrelenting curiosity and ambition to explore the unknown. Proxima B, a world of contrasts. Proxima B is a planet of stark contrasts, a world where extremes define its very existence. Roughly 1.17 times the mass of Earth, it is tantalizingly similar in size to our own planet, making it a prime candidate for habitability studies. Its orbit within the habitable zone of Proxima Centauri, the region where liquid water could theoretically exist, further fuels speculation about its potential to support life. Liquid water is a cornerstone of life as we know it, and the possibility of its presence on Proxima B has scientists buzzing with excitement. However, Proxima B's similarities to Earth end where its environment begins. Orbiting a red dwarf star, Proxima Centauri, which is only about 12% the mass of our Sun and significantly cooler, Proxima B experiences a radically different stellar environment. Red dwarfs are the most common stars in the Milky Way, comprising roughly 75% of the galaxy's stellar population. Their small size and low luminosity mean their habitable zones are much closer to the star than in our solar system. For Proxima B, this translates to an orbit just 7.5 million kilometers from its star, about 5% of the distance between Earth and the Sun, completing a full orbit in a mere 11.2 Earth days. This close proximity results in one of Proxima B's most defining features, tidal locking. Much like the Moon always shows the same face to Earth, Proxima B is likely tidally locked to its star, with one hemisphere perpetually bathed in starlight and the other shrouded in eternal darkness. The day side could experience scorching temperatures, potentially exceeding 200 degrees Celsius in some models, while the night side might plummet to below -200 degrees Celsius. These extreme temperature gradients pose significant challenges for life, as they could create a planet of stark climatic divides. Yet there is hope in the twilight zone, a narrow band between the searing day side and the frozen night side, where temperatures might be more temperate. In this region, conditions could theoretically allow for liquid water, creating a potential oasis for life. Models suggest that if Proxima B has an atmosphere capable of redistributing heat, this twilight zone could maintain stable conditions, offering a glimmer of hope for habitability. However, the planet's ability to sustain such an atmosphere is uncertain, given the intense radiation and solar flares from Proxima Centauri, which could strip away atmospheric layers over time. The hostile environment of Proxima B is further complicated by its star's volatility. Red dwarfs like Proxima Centauri are prone to frequent and powerful solar flares, which unleash bursts of X-rays and ultraviolet radiation. These flares could bombard Proxima B, potentially eroding its atmosphere and exposing its surface to harmful radiation. For life to survive, it would need to be exceptionally resilient, perhaps thriving in subsurface oceans, shielded caves, or other protected niches. Alternatively, life forms could have evolved unique adaptations to cope with such harsh conditions, challenging our Earth-centric assumptions about biology. Despite these challenges, Proxima B's proximity to Earth, just 4.2 light-years or roughly 40 trillion kilometers, makes it an unparalleled opportunity for study. Unlike more distant exoplanets, Proxima B is close enough to be observed with current and near-future technologies, offering a rare chance to probe the characteristics of an Earth-like world. Its discovery has opened a new chapter in astronomy, one where the dream of finding extraterrestrial life feels closer than ever. Red dwarfs, the unsung heroes of habitability. To understand Proxima B, we must first understand its host star, Proxima Centauri, and the broader role of red dwarfs in the search for life. Red dwarfs, or M-dwarf stars, are the most abundant stellar type in the galaxy, yet their small size and dim glow often make them overlooked compared to brighter stars like our Sun. With masses ranging from 8% to 60% of the Sun's, red dwarfs burn their nuclear fuel slowly, resulting in lifespans that can exceed 100 billion years, far longer than the Sun's projected 10 billion-year lifespan. This longevity provides a stable energy source for orbiting planets, potentially allowing life to develop over vast timescales. The habitable zones of red dwarfs are uniquely positioned due to their low luminosity. Unlike the Sun, whose habitable zone lies between roughly 0.8 and 1.5 astronomical units, AU, red dwarfs have habitable zones much closer to the star, often within 0.1 astronomical units. This proximity allows planets like Proxima B to receive sufficient energy to support liquid water despite the star's faint output. However, this closeness comes with trade-offs. Planets in these tight orbits are more likely to be tidally locked, and their exposure to stellar activity such as flares increases the risk of atmospheric loss. Red dwarfs' stability over billions of years makes them intriguing candidates for hosting life, but their volatility presents significant hurdles. Solar flares from Proxima Centauri, for instance, can increase the star's brightness by orders of magnitude, bathing nearby planets in intense radiation. Recent studies, including observations from the Transiting Exoplanet Survey satellite, TESS, in 2024, have confirmed that Proxima Centauri experiences flares as frequently as every few hours, with major events capable of delivering radiation doses thousands of times stronger than those experienced on Earth. Such conditions could sterilize the unprotected surfaces, making atmospheric retention a critical factor for habitability. Despite these challenges, red dwarfs dominate the exoplanet landscape. Of the over 5,500 exoplanets confirmed, as of 2025, a significant portion orbit red dwarfs, thanks to their abundance and the relative ease of detecting planets in their close-in habitable zones. Proxima B, as the closest known exoplanet to Earth, exemplifies the potential and pitfalls of these systems. Its discovery has spurred renewed interest in red dwarf planets, prompting missions to identify other nearby candidates. For instance, the Speculoos, Search for Planets Eclipsing Ultra-Cool Stars project, ongoing in 2025, targets ultra-cool dwarfs to find Earth-like planets, building on the success of discoveries like the TRAPPIST-1 system. The study of red dwarfs is not just about finding life. It's about redefining our understanding of habitability. These stars challenge the notion that life requires a sun-like environment, suggesting that the universe may be teeming with planets capable of supporting life in ways we have yet to imagine. Proxima B, as a flagship red dwarf planet, is at the forefront of this paradigm shift, offering a testing ground for theories about life in extreme environments. The mystery of Proxima B's light emissions. At the heart of Proxima B's allure lies a discovery that has sent shockwaves through the astronomical community: unusual light emissions detected from the planet's dark side. First reported in 2023 by a team using the James Webb Space Telescope, JWST. These emissions defy conventional explanations, raising the tantalizing possibility of extraterrestrial origins. Unlike typical planetary emissions, which are often tied to reflected starlight or atmospheric processes, these signals appear to originate from the perpetually shadowed hemisphere, where no starlight reaches. The emissions observed in the infrared spectrum exhibit patterns that do not align with known natural phenomena, such as volcanic activity, auroral displays, or atmospheric scattering. Preliminary analyses suggest they could be artificial in nature, a potential signature of advanced technology, such as a Dyson swarm, megastructures, or even a beacon from an intelligent civilization. While such interpretations are speculative, they have galvanized the scientific community, prompting urgent calls for follow-up observations. The implications of these emissions are profound. If they are indeed artificial, they could represent the first evidence of extraterrestrial intelligence, a discovery that would reshape humanity's worldview. Even if natural, the emissions suggest that Proxima B harbors unique geological or atmospheric processes, offering new insights into exoplanet science. For instance, some researchers propose that the signals could result from cryovolcanism, ice-driven volcanic activity on the cold night side, or from exotic atmospheric chemistry driven by stellar radiation. Regardless of their origin, the emissions have elevated Proxima B to a top priority for observation. To investigate further, astronomers are leveraging the full capabilities of JWST, which as of 2025 remains the most advanced tool for studying distant exoplanets. Its near-infrared spectrograph, NIR spec, and mid-infrared instrument, MIRI, are ideally suited to analyze Proxima B's atmosphere and surface, potentially identifying chemical signatures like water vapor, methane, or even technosignatures, indicators of technological activity. Additionally, the upcoming Extremely Large Telescope, ELT, set to begin operations in 2028, will deploy the Harmony instrument to provide unprecedented resolution, allowing scientists to distinguish planetary signals from stellar noise. The challenge lies in separating Proxima B's faint emissions from the overwhelming glare of Proxima Centauri. Techniques like high-contrast imaging and coronagraphy, which block starlight to reveal orbiting planets, are being refined to improve data quality. Meanwhile, machine learning algorithms are being employed to analyze spectral data, identifying subtle patterns that might indicate biological or technological activity. These efforts underscore the interdisciplinary nature of the search for life, blending astronomy, physics, chemistry, and artificial intelligence. Technological challenges and future prospects. Studying Proxima B is no small feat. At 4.2 light-years, or approximately 40 trillion kilometers, the planet is beyond the reach of current spacecraft. Even with the fastest theoretical propulsion systems, such as laser-driven light sails proposed by the Breakthrough Starshot initiative, a journey to Proxima B would take 20 to 30 years, with data transmission adding another 4.2 years. For now, our exploration is limited to remote observations, relying on telescopes and instruments that push the boundaries of human ingenuity. The primary obstacle is distance. Proxima B's faint signal is drowned out by the brightness of its host star, requiring telescopes with exquisite sensitivity. The JWST, launched in 2021, has revolutionized exoplanet studies with its ability to capture infrared light, which is critical for analyzing cool, distant worlds like Proxima B. Its observations have provided the first detailed spectra of the planet's atmosphere, hinting at the presence of water vapor and carbon dioxide. However, JWST's resolution is limited, and its observations are often hampered by stellar flares, which introduce noise into the data. To overcome these limitations, astronomers are developing next-generation instruments. The ELT, under construction in Chile, will feature a 39-meter primary mirror, nearly 4 times the diameter of JWST's, offering unmatched light-gathering power. Its Harmony instrument will enable direct imaging of Proxima B, potentially revealing surface features or atmospheric dynamics. Similarly, the large ultraviolet optical infrared surveyor, LUVOIR, a proposed NASA mission for the 2030s, aims to study exoplanet atmospheres with unprecedented precision, targeting biomarkers like oxygen and methane. Another challenge is Proxima B's tidal locking and extreme environment. The planet's day side is likely too hot for liquid water, while the night side is too cold. The twilight zone, where conditions might be habitable, is difficult to observe due to its narrow extent and the planet's faint reflectivity. Stellar flares further complicate matters, as they can temporarily alter atmospheric chemistry, masking potential biosignatures. To address this, scientists are modeling Proxima B's climate using supercomputers, simulating how heat and radiation interact with its atmosphere. These models, updated in 2025, suggest that a thick atmosphere or subsurface ocean could mitigate temperature extremes, enhancing habitability. Looking ahead, the search for life on Proxima B will rely on a combination of technological innovation and international collaboration. Projects like the Square Kilometre Array, SKA, set to begin operations in the late 2020s, will scan the cosmos for radio signals, including potential technosignatures from Proxima B. Meanwhile, citizen science initiatives, such as the SETI at Home Reboot in 2024, engage the public in analysing data, amplifying the search effort. These endeavours reflect a global commitment to uncovering the truth about Proxima B and its place in the universe. The discovery of life on Proxima B, whether microbial, complex or intelligent, would be a watershed moment in human history. Biologically, it would expand our understanding of life's adaptability, revealing how organisms might thrive in environments vastly different from Earth's. For instance, life on Proxima B might rely on alternative biochemistries, such as methane-based metabolism, challenging the primacy of water as a solvent for life. Such a discovery would inform astrobiology, guiding the search for life on other exoplanets and moons, like Europa or Enceladus. Technologically, evidence of an advanced civilization would revolutionize our approach to science and engineering. If the light emissions are indeed technosignatures, they could indicate energy harvesting structures, communication networks, or even interstellar probes. Reverse engineering such technologies could accelerate human innovation, from energy production to space travel. Philosophically, the discovery would force us to confront existential questions about our uniqueness, our purpose, and our responsibility as a species. The societal impact would be equally profound. Confirmation of alien life could unite humanity in a shared quest for knowledge, fostering global cooperation. Conversely, it could spark ethical debates about how to interact with extraterrestrial beings or whether to broadcast our presence. Organizations like the United Nations Office for Outer Space Affairs are already preparing protocols for such scenarios, updated in 2025, to address the growing likelihood of contact. Even if Proxima B's emissions are natural, the planet remains a treasure trove of scientific opportunity. Its study will refine our models of exoplanet atmospheres, informing the search for other habitable worlds. It will also drive innovation in telescope design, data analysis, and propulsion technologies, paving the way for future missions to nearby stars. Proxima B, in essence, is a catalyst for human progress, pushing us to expand our horizons and embrace the unknown. As we peer deeper into the mysteries of Proxima B, the stakes could not be higher. The planet's Earth-like traits, coupled with its enigmatic light emissions, make it a beacon of hope in the search for life. Yet the challenges are formidable. Distance, stellar interference, and technological limitations all stand in our way. Fortunately, the tools of modern astronomy are evolving rapidly, with JWST, ELT, and future missions like LUVOIR poised to unlock new insights. The next decade will be critical. By 2030, we may have definitive evidence of Proxima B's atmospheric composition, surface conditions, and potential biosignatures. If the light emissions are confirmed as technosignatures, humanity will face a paradigm shift unlike any in history. Even if they are natural, Proxima B will continue to teach us about the diversity of planetary systems and the resilience of life. For now, Proxima B remains a distant enigma, a world of extremes and possibilities. Its twilight zone, where day meets night, symbolizes the boundary between the known and the unknown. As we refine our telescopes, sharpen our algorithms, and dream of interstellar voyages, we inch closer to answering the question that has haunted us for centuries. Are we alone? Proxima B may hold the key, and the journey to uncover its secrets is just beginning. Stay tuned, for the cosmos is full of surprises, and Proxima B is only the start.